Okay, we're going to do a little tutorial today on drawing ray diagrams with mirrors. I wrote down here the three main rays you want to think about when we're doing curved mirrors are in parallel, out through the focal point, in through the focal point, out parallel, and in through the center and back. I thought I'd start though with a flat mirror, and keep in mind that all of these mirrors are governed by the principle of the law of reflection, which says that if a ray comes in and then it bounces off, the angle of incidence, right here, is going to equal the angle of reflection. When you draw the normal to the surface, those two angles are going to be the same. And so every ray will be governed by that principle. So let's take a look at the case where we have a person and you have a flat mirror and they are looking at their foot. Well, where is the image going to be, or what's going on? So the idea is that a ray of light is coming from the foot and is going up towards the mirror, and then it bounces and goes into the eyeball. So the person sees that toe. Now, once again, if you have your normal, then the angle of incidence equals the angle of reflection. And the reason that we actually see an image on the other side of the mirror is because if you take this ray that's going towards the eyeball and you back it up, it will appear to come from behind the mirror. So light rays that coming into your eyeball doesn't see that the rays bounce. It thinks that the ray came from a straight line, in this case behind the mirror. And so that's where it would see the image of the toe. So it turns out that oops, I went too far, my bad. It turns out that for a flat mirror, the distance from the mirror is going to be the same as the distance behind the mirror. So these two distances are going to be the same. It also turns out that the height of the image behind the mirror is going to be the same as the height of the image on the original side of the mirror. We call this as the image, and we say it is a virtual image. It is upright and behind the mirror, and that'll become important when we get to the curved mirrors. Okay, moving on. All right, so now we've got a curved mirror. This is a concave mirror, and the purple dot represents the center of the mirror. The F represents the focal point. And then we have our object, which is outside the center. And we want to locate the image, and so we're going to draw three rays. The first one is going to go in parallel and then bounce off the mirror, angle of incidence equals angle of reflection, to go through the focal point. So in parallel, out through the focal point. The next one is going to go in through the focal point and out parallel. And then the final one goes through the center and back. And conveniently in our little diagram, all three of these have the same convergence point right here. They come together. When light rays converge with a mirror, then you have what's formed is a real image. And so we can locate it. Looks like this. Now it looks like the image is inverted, meaning it's upside down, and it is minified. It is shrunk a little bit. And we can figure out exactly how much it's shrunk if we do the math based on where the object distance was to start. So let's go ahead and do that. I've set up my same little scenario. I'm gonna leave out the ray diagrams just to make it a little neater, but we're gonna do the math. So we're gonna say the object is 5 centimeters high. It's 30 centimeters measured from the mirror, and the focal length is 10 centimeters. So if we have our lens equation, 1 over f equals 1 over p plus 1 over q, we plug those in. We get 1 over 10, that's the focal point, is 1 over 30 plus 1 over q. We solve and get q is 15 centimeters. So now we can find the magnification. Remember our image, I just tried to put it back to where it was from the slide before, is going to be minus q over p. So we can say the magnification is negative 15 over 30, which is negative 1/2. If we want to plug in the rest of the values, we can solve and get that the new height is negative 2.5 centimeters. I do want to point out when you have the magnification is negative 1/2, that 1/2 is what represents the fact that it is shrunk. If it was like a value of negative 3, that means it would be 3 times larger. It would be magnified. The negative sign indicates that the image is inverted or upside down. If that number were positive, then the image would be upright. But as you can see, our image is upside down. Okay, now we're going to move on to the next lens. In this case, we have a Concave lens also, except this time we've moved the object to be inside the focal length. So let's look at the three images. Here we go. I'm sorry, the three rays. We're going to go in parallel and then out through the focal point. That's the first ray. The next one's a little trickier because we're going to go from the focal point out parallel, but we have to start at the focal point, work our way through the arrow, hit the mirror, and then bounce out parallel. Now what you notice is, right away, these two rays are diverging. They are not going to intersect. So we know right away we're not going to get a real image. Let's do the third ray though. It's going to go in through the center and back. So to find the image, we figure out, well, where did these rays appear to come from when they bounced? And so we're going to take the outgoing rays and we're going to back them up. So we take that outgoing ray of the blue ray and we back it up and say, where did it appear to come from? And then we do the same thing with the purple ray and the same thing with the green ray, and all three rays intersect, and that is where our image is located. In this case, it's upright. Therefore, we know it's virtual. It is behind the mirror. It's also magnified. But we look at the Q value. Like if we're going to run the math on this one, which we're not going to do, then you would solve, when you solve for your focal length and your object distance, P, you would get that Q is negative because Q is the actual image is behind the mirror. And your magnification, by the same token, remember if magnification is minus Q over P, and if Q is negative, then the magnification is going to be positive, which is going to tell you that it is upright. In this case, it looks like it's actually going to be magnified. It would be like a magnification of, it looks like it's almost double based on this scale of this drawing. So the magnification would be about +2, something like that. Okay, let's move on to talk about a convex mirror. In a convex mirror, the focal length is actually behind the mirror, and so we say that the focal length is going to have a negative value. So we go ahead and draw our rays, which I've already done. I've got two sets. I'm going to go in towards the focal point and then out parallel, and then I'm going to go in parallel and out as if it's coming from the focal point. So right away you can see that those two rays are diverging, so we know right away we're going to get a virtual image, which we always get with a convex mirror. There's no way to get a real image with a convex mirror. And through the center and back. So there's the three rays. So we're going to back them up and see where they come together. There's one, there's two, and so therefore there's your image. So the image is going to be minified, which is always the case with a convex mirror. You know, objects in the mirror appear larger than they actually are. That's what your mirror on your car is, a convex mirror. And so we could then run the lens equations for this as well, and we're going to get, again, Q is negative. The focal length is negative, so Q is going to be negative. This one looks minified, so you can run the numbers. And that concludes our tutorial.